Okay, well, all right. Here we are, and yet another video. This time it's going to be a delightful functional equation. Uh, I know that this problem is incredibly difficult. No, it's not. But we'd like to believe that we can do something about this problem. So the problem says that here's a function which is defined from set of naturals to set of rationals, such that this is true, and then we have to evaluate this. Well, the first question which I'm going to ask is that. Uh, is there a way to find the function? And what's also given is that f of 1, it's given to you as 3 by 2, like this implicit. So it's given that f of 1 is in fact 3 by 2. Uh, so the question that I'm asking here at this point is that can we explicitly find the function? And also, if you look at it this way, this is uh, kind of annoying in the way that here is x plus 1, there is y plus 1. So y is given like that. So, well, let's do some algebra. You can say that f of x plus y is in fact equal to, after some simplification, that x plus y plus 1 times fx upon x plus 1 plus f of y upon y plus 1. And that's that. And plus xy plus x plus y plus 1. And you notice that this number x plus y plus 1 features everywhere. And since x and y are natural numbers, x plus y plus 1 is essentially positive. So we can divide by x plus y plus 1 to get that f of x plus y upon x plus y plus 1 is equal to f of x upon x plus 1 plus f of y upon y plus 1 plus xy. Right, and if you were to, you can see that there is a definite function which is sort of repeating itself every time. So I'm going to define that function. So let g of t be f of t upon t plus 1. So this problem becomes g of x plus y is equal to g of x plus g of y plus xy. That is what you eventually get. And now the question which I'm asking of myself is that, well, uh, this is almost Cauchy's functional equation. So if you were to eliminate this part, this would be Cauchy's functional equation. We could have said that, well, gx is going to be cx, but that's not going to be true this time. So the next obvious thing to do is that now I'm going to ask myself that can I guess this function, what g of x is? Because if I can guess that this is g of x, then I can find out f of x, right? And why? Because f of x is something like that. And yet there will be another question that how do we know that this is the only g of x that can satisfy the given equation, right? So we will not be absolutely sure that this is the function g of x that will satisfy this, even if it does, but we will be somewhat very closer to the answer. So now I'm going to take a guess that what kind of function g would be, that what is g of x actually. So well, uh, obviously, had this been the case, if this were the problem, g of x would have been linear. Since I see a degree 2 term here, so I'm going to hazard a guess that g of x is a 2-degree polynomial. And the simplest of 2-degree polynomial to try would be x squared. So the question they were asking is that is g of x x squared? So well, so this number is x plus y squared if g of x is x squared, and this is x squared, and this is y squared, and this is xy. And then you can see that this doesn't work. Because if g of x were x squared, you still have an extra xy. And then immediately it occurs to you that what if you were to choose g of x as x squared by 2? So if g of x is x squared by 2, so this number is x plus y squared by 2. This number is half x squared. This number is half y squared, and this is xy. And then this equation holds perfectly fine. Well, that doesn't mean that g of x is essentially x squared. But it does tell you that that doesn't mean that g of x is x squared by 2, but it does tell you that x squared by 2 is indeed one of the functions which satisfies this equation. And if you want to actually prove that g of x is x squared by 2, then I'm going to define a new function, the difference function, which is g of x minus x squared by 2, and I'm going to call it as h of x. So what happens now is that this functional equation now transforms into, so g of x plus y is going to be h of x plus y plus half x plus y squared. This is going to be equal to g of x plus half of x squared. That's going to be g of y plus half y squared and plus xy. Right, and now you can see that this half x squared, half y squared, and half x and xy, they all get cancelled with half of uh, x plus y squared. And what you eventually get is, in fact, what we are aiming for. So you get h of x plus y is equal to h of x plus h of y. And that tells you that h is Cauchy's functional equation. And that tells you that hx will be equal to cx. Now, I'm not going to prove it because this is standard Cauchy's functional equation, right? And well, when we're done with this, so what you eventually get is that, well, how do you find c? Well, c is simply h of 1. So if we can find h of 1, we are done, right? So we'll be able to find h, and then we'll be able to find g, and therefore f. So c is h of 1. Now h of 1, using this equation, is simply g of 1 minus 1 by 2. So h of 1 is simply g of 1 minus 1 by 2. And what's g of 1? Well, g of 1 is f of 1 upon 2. And f of 1 is given to you as 3 by 2. So that number is going to be 3 by 4. So therefore, it's 3 by 4 minus 1 by 2, which is equal to 1 by 4. So now we know that h of x is in fact 1 by 4x. And that tells you that g of x is equal to x squared by 2, x squared by 2 plus hx, and hx was x by 4. Right, something like that forming. Now that we have found out gx, so the question is that can we find out fx? Obviously we can, because we have argued that f of x was x plus 1 times g of x. So that's what you eventually get. And yeah, something like that. X squared by 2, in fact. So I just did the other way around. So it should be x squared by 2 and that. So now that we have explicitly found out f, we can always find that limit n tends to infinity, f of n upon n cubed is going to be n plus 1 into n squared by 2 plus 1 by 4 upon n cubed, and which is equal to 1 by 2, and we are done.